Real numbers. CBSE Class 10 Maths Chapter 1 Notes. Real numbers. R stands for real numbers. All rational and irrational numbers are called real numbers. I stands for integers. All numbers from -3, -2, -1 or even before that and 0, 1, 2, 3 and after that are called integers. Q stands for rational numbers. Real numbers of the form P divided by Q, where Q is not equal to 0 and P and Q belongs to 1 are rational numbers. All integers can be expressed as rational. Decimal expansion of rational numbers terminating or non-terminating recurring. Q, comma is irrational numbers, real numbers that cannot be expressed in the form of PQ and whose decimal expansion are non-terminating and non-recurring. Root of primes like root 2, root 3, root 5, etc. are irrational. N is called as natural numbers. Counting numbers are called natural numbers. N equal to 1, 2, 3, etc. Whole numbers stands for W. 0 along with all natural numbers are together called as whole number. 0, 1, 2, 3, etc. Even numbers. Natural numbers of the form 2n are called even numbers. 2, 4, 6, etc. Odd numbers. Natural numbers of the form 2n minus 1 are called odd numbers. 1, 3, 5, etc. Why can't we write the form as 2n plus 1? Remember this. All natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. All rational numbers are real numbers. Prime numbers. The natural numbers greater than 1 which are divisible by 1 and the number itself are called prime numbers. Prime numbers have two factors, that is 1 and the number itself. For example, 2, 3, 5, 7 and 11 etc. 1 is not a prime number as it has only one factor. Composite numbers. The natural numbers which are divisible by 1 itself and any other number numbers are called composite numbers. For example, 4, 6, 8, 9, 10, etc. Note, 1 is neither prime nor a composite number. Real numbers. Euclid's division lemma. Give two positive integers a and b. There exist unique integers q and r satisfying a equal to bq plus r, where 0 less than or equal to r less than or equal to b. Notice this, each time r is less than b, each q and r is unique. Application of lemma. Euclid's division lemma is used to find HCF of two positive integers. For example, find HCF of 56 and 72. Steps. Apply lemma to 56 and 72. Take bigger number and locate B and R. 72 equal to 56 into 1 plus 16. Since 16 is not equal to 0, consider 56 as the new dividend and 16 as the new divisor. 56 equal to 16 into 3 plus 8. Again, 8 is not equal to 0. Consider 16 as new dividend and 0 as new divisor. 16 equal to 8 into 2 plus 0. Since remainder is 0, divisor 8 is HCF. Although Euclid's division lemma is stated for only positive integers, it can be extended for all integers except 0, that is b is not equal to 0. Constructing a factor tree. Here are the steps. Write the number as a product of prime number and a composite number. For example, let's factorize 48. Repeat the process till all the primes are obtained. Therefore, prime factorization of 48 equal to 2 raised to 4 into 3. Fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this expression is unique apart from the order in which they appear. Here are some applications. To locate HCF and LCM of two or more positive integers, to prove the irrationality of numbers, to determine the nature of the decimal expansion of rational numbers. Algorithm to locate HCF and LCM of two or more positive integers. Step 1. Factorize each of the given positive integers and express them as a product of powers of primes in ascending order of magnitude of primes. Step 2. To find HCF, identify common prime factor and find the least powers and multiply them to get HCF. Step 3. To find LCM, find the greatest exponent and then multiply them to get the LCM. So how to prove the irrationality of numbers? The sum or differences of a rational and an irrational number is irrational. The product or quotient of a non-zero rational number and an irrational number is irrational. To determine the nature of the decimal expansion of rational numbers, let x equal to p divided by q. P and q are coprimes. Be a rational number whose decimal expansion terminates. Then the prime factorization of q is of the form 2 raised to m 5 raised to n, where m and n are non-negative integers. Let x equal to p divided by q be a rational number such that the prime factorization of q is not of the form 2 raised to m 5 raised to n, where m and n being non-negative integers. Then x has a non-terminating repeating decimal expansion.